Thank you. It's my great honor and pleasure to speak here. I'll talk about weighted Fourier extension estimates and applications. Here's an overview. I'll first introduce Carson's pointwise convergence problem. A standard method to approach this problem is through Schrödinger maximal estimates. And we'll compare such estimates with the Fourier restriction conjecture, which is a central open problem in harmonic analysis. In the second part, we'll see a generalization of the Schrödinger maximal estimates. That is, the so-called weighted Fourier extension estimates. And these estimates have applications to several problems in PDEs and geometric measure theory, including the divergence set of Schrödinger solutions, the spherical average Fourier decay rates of fractal measures, and the Falconer's distance set problem. Let's first recall the Fourier transform and its inverse. Given an integrable function g in space, we can define its Fourier transform g hat in frequency using this integral here. And the Fourier inversion formula said that we can recover the function g from its Fourier transform g hat using this inverse Fourier transform integral. Now let's see Schrödinger solutions. Consider this free Schrödinger equation. Here x is a space variable in Rn, t is a time variable in R. The equation is I du by dt plus Laplacian u equals 0. And when t equals 0, the initial data is f. We can apply Fourier transform to this equation and turn it into an ODE and get that u hat of c t given by f hat of c e to the it c squared. Therefore, by Fourier inversion formula, the formal solution u of xt is given by the inverse Fourier transform of this expression. Okay. And by convention, we denote this solution by e to the it Laplacian f of x. It is a solution to the free Schrödinger equation with initial data f. Here are some basic properties about the Schrödinger solutions. First, we have conservation of energy. That is, at any fixed time t, the L2 norm of the solution with respect to the x variable stays the same as the L2 norm of the initial data. Also, it's easy to prove convergence in L2. For any initial data f in L2, as t goes to 0, the solution converges to the initial data in L2 norm. However, for pointwise convergence, it's tricky. We hope for this property. As t goes to 0, the solution converges to f of x for almost every x with respect to the bigger measure. But this pointwise convergence property fails for certain L2 functions f. So another natural question to ask is what regularity of the initial data is required to ensure pointwise convergence of Schrödinger solutions? And to quantify this regularity, we use Sobolev spaces. Recall that for an integer k, the Sobolev space hk of Rn is a subspace of L2. It consists of the L2 functions f, such that all these derivatives of f up to order k are also L2 integrable. And this integer k represents the order of weak differentiability. There is an equivalent definition. A function f is in hk if and only if this integral here is finite. And we denote this quantity by the hk Sobolev norm of f. The advantage of this equivalent definition is that in this expression, we can replace the integer k by any real number s and use it to define the Sobolev space Hs over Rn. Here, the real number s represents the order of regularity. Okay. Now we are ready to talk about the pointwise convergence problem of Schrödinger solutions. This question was raised by Carlson in 1979. It is to determine the minimal regularity S, such that if the initial data F is in the Sobolev space Hs of Rn, then the pointwise convergence holds. More precisely, as t goes to 0, the solution converges to f of x for almost every x with respect to the bigger measure. And for convenience, we denote this desired property by PC, short for pointwise convergence. Carlson himself proved that when n equals 1, the pointwise convergence holds for s greater than or equal to 1/4. And 2 years later, Dalberg and Koenig showed that Carlson's result is optimal. They constructed an example showing that the pointwise convergence can fail if s is smaller than 1/4 in any dimension. So the question with n equals 1 was resolved. Now let's see the progress on this pointwise convergence problem in higher dimensions. On this page, the numbers in blue are sufficient conditions, and the numbers in red are necessary conditions. Let's see. In late 80s, Herlin and Figa independently proved pointwise convergence for s greater than 1/2 in any higher dimension. And this result was further improved by several different authors. In particular, in 2006, Sang-Hyuk Lee proved pointwise convergence for s greater than 3/8 when n equals 2. Later, in 2012, Bourgain proved pointwise convergence for s greater than 1/2 minus 1/4n in any dimension. And when n equals 2, this number is 3/8. It recovers this result using a different method. And before Bourgain's work, for a long time, people believed that 1/4 should be the sharp endpoint for pointwise convergence in every dimension. However, in this paper, Bourgain constructed an example showing that this is no longer true when s is small for large n. The pointwise convergence can fail if s is smaller than 1/2 minus 1/n when n is greater than 4. And this was further improved by Luca and Rogers, Dimitar and Guo. In 2016, Bourgain constructed another delicate example, showing that the pointwise convergence can fail if s is smaller than n/2 times n plus 1 in any dimension. And if we compare this necessary condition with this sufficient one, we see that there is still a gap. For example, when n equals 2, this number is 1/3. It is smaller than 3/8. After this, joined with others, we prove that Bourgain's example is sharp up to the endpoint. When n equals 2, this result is a joint work with Larry Guth and Xiumin Li. And the result in any higher dimension is a joint work with Xiang Zhang. So now the pointwise convergence problem has been solved in every dimension up to the endpoint. The resolution of this problem uses deep results and techniques about the Fourier restriction conjecture in harmonic analysis. So next, I'll briefly introduce the Fourier restriction conjecture. This problem was raised by Stein in 1970s. Consider this. Suppose H is an R1 function on Rn. Then we know that its Fourier transform H hat is a continuous and bounded function. So we can restrict H hat onto any subset of Rn and get a meaningful function on that subset. Now suppose H is an L2 function. Then its Fourier transform is also an L2. And we know that the Fourier transform is a bijection between L2 functions. So here, this H hat can be an arbitrary L2 function. And in this case, there is no meaning to restrict H hat onto a subset of zero Lebesgue measure. Now, what happens if H is an LP function, where P is strictly between 1 and 2? The question is that, given an LP function H, can we meaningfully restrict its Fourier transform H hat onto a subset of zero Lebesgue measure? Well, Stan observed that if that subset is a hypersurface with non-vanishing curvature, then the answer is yes. After restriction, H hat on that hypersurface is some LQ function for some Q depending on P. And this question is a central and a fundamental problem in harmonic analysis. It's closely related with several other open problems, including Kakeya, Falconer rays, and local smoothing conjectures. To be explicit, let's consider the Fourier restriction problem for the truncated paraboloid. Here we use S to denote the truncated paraboloid, Cc, Cc squared, where Cc is in the n-dimensional unit ball. And the surface measure, d sigma, is given by the pullback of the Lebesgue measure on its projection onto the unit ball. And the Fourier restriction conjecture asks for sharp LP to LQ estimates about this Fourier restriction operator, which sends a function H to its Fourier transform restricted onto the hypersurface. And by duality, this is equivalent to proving some sharp LQ prime to LP prime estimates about the dual operator, which we call the Fourier extension operator. This operator sends a function G on the surface to the inverse Fourier transform of the surface measure, GD sigma. Now recall Schrödinger solutions. E to the it Laplacian f of x is given by this integral, and we can write it as inverse Fourier transform of the surface measure f hat d sigma on the paraboloid. So the Schrödinger solutions can be viewed as the Fourier extension operator over the paraboloid. And the progress on this Fourier restriction conjecture gives us important tools for solving the pointwise convergence problem of Schrödinger solutions. Here are several landmarks that influence the progress on pointwise convergence problem. The first is the bilinear restriction method developed by Wolf and Tao. This bilinear restriction method is essential in the Sanghill-Klees work, where he proved pointwise convergence for s greater than 3/8 when n equals 2. And after bilinear restriction, Bennett, Carberry, Tao proved multilinear restriction estimates. And in this joint work by Bourgain and Guth, they developed a technique passing from multilinear restriction estimates to a linear one, using induction on dimensions and different scales. And this technique is essential in Bourgain's work, where he proved a pointwise convergence for s greater than 1/2 minus 1/4n for any n. After that, there were two breakthroughs related to Fourier restriction problem. One is the proof of L2 decoupling theorem by Bourgain and Demeter. Another one is the introduction of the polynomial partitioning method to the Fourier restriction problem by Guth. And these two works are essential in our final resolution of the pointwise convergence problem. Now let's see how to approach the pointwise convergence problem. We want to prove that as t goes to 0, the solution converges to f of x almost everywhere for any initial data f in the Sobolev space Hs of f. And here we can use a smooth approximation argument. Suppose the function f is a Schwarz function. Then the pointwise convergence holds uniformly because f is rapidly decaying. Okay. Well, the Schwarz space is dense in Hs. So in order to prove the pointwise convergence for all Hs functions, it's sufficient to show that the associated maximal function is bounded from Hs to some LP space. And after some reductions by Littlewood-Paley decomposition, parabolic rescaling, and a localization argument using field packets, which was observed by Sanghyul Lee, the problem was eventually reduced to an estimate of this form, which we call Schrödinger maximal estimate. It said that for any function f with Fourier transform supported in the n-dimensional ball of radius 1, we have this estimate. This Schrödinger maximal function here, the supremum of the absolute value of the solution over the time interval from 0 to r, has its L2 norm over the n-dimensional R ball, essentially bounded by R to the S0 FL2. Here, R is a large parameter, and this symbol means that we are allowed to lose an arbitrarily small power of R. So for Schrödinger maximal estimate of this form, where on left-hand side we have the L2 norm, and on right-hand side the exponent is S0. This Schrödinger maximal estimate implies pointwise convergence for S greater than S0. Here are our main results on Schrödinger maximal estimates. When n equals 2, joint with Larry Guth and Xiaochen Li, we proved this L3 Schrödinger maximal estimate. It said that the L3 norm of the Schrödinger maximal function over the two-dimensional R ball is bounded by FL2. And if we want to bound this L2 norm, we just go from L2 to L3 using Holder and get this power of R times FL2. And this here, the exponent of R is 1/3. So this estimate implies the pointwise convergence for S greater than 1/3 when n equals 2. In higher dimension, joint with Xiang Zhang, we proved this L2 Schrödinger maximal estimate, which said that the L2 norm of the Schrödinger maximal function over the n-dimensional ball of radius R is bounded by R to this sharp exponent n over 2 times n plus 1 FL2. When n equals 2, this estimate is the same as the one here, but it is not as strong as the L3 Schrödinger maximal estimate. Okay. Next, we'll compare Schrödinger maximal estimates with the Fourier restriction conjecture. For that purpose, we'll use the locally constant property. The locally constant property roughly said that for a function f with Fourier transform supported in the n-dimensional ball of radius 1, the absolute value of the solution is essentially a constant on any unit cube in dimension n plus 1. More precisely, on this unit cube B, this L1 norm here is bounded above by its L infinity norm because the volume of B is a constant. While on the other hand, the L infinity norm is bounded by L1 norm with respect to some weight adapted to B. This weight is approximately 1 on B and rapidly decaying off it. So over this unit cube B in dimension n plus 1, all these LP norms are essentially equivalent. Therefore, for integral purpose, we can feel the absolute value of Schrödinger solution as a constant on any unit cube. Now let's compare the Schrödinger maximum estimate and the Fourier restriction conjecture. This is the L3 Schrödinger maximum estimate we proved. It said that the L3 norm of the Schrödinger maximum function over the two-dimensional ball of radius r bounded by FL2. And this is the Fourier restriction conjecture in dimension 3, which said that the regular L3 norm of the Schrödinger solution over the three-dimensional R ball is bounded by f hat L infinity. Note that these two expressions are similar. Let's compare them. Consider the terms on left-hand side. This one here is a mixed L3 L infinity norm, while this one is a regular L3 norm. By locally constant property, the absolute value of the Schrödinger solution is essentially constant on any unit cube. So this mixed norm is bounded above by the regular L3 norm. Okay. And for the terms on right-hand side, FL2 equals F hat L2 by Planck's law. And because F hat has a compact support, so its L2 norm is bounded above by its L infinity. Okay. So by these comparisons, this term is smaller than this one, and this term is smaller than that one. So one estimate is not stronger than the other. So far, we have proved the L3 Schrödinger maximum estimate. However, the Fourier restriction conjecture still seems far out of reach. Now let's consider it in higher dimensions. Recall that in higher dimensions, we only have the sharp L2 Schrödinger maximum estimates. Well, for Fourier restriction conjecture, in dimension n plus 1, the sharp endpoint is 2 times n plus 1 over n. And it seemed possible that at this sharp endpoint, we should have a similar Schrödinger maximum estimate. We denote this by conjecture. In a summer workshop, joint with Zhongcheng Kim, Hong Wang, and Ruixiang Zhang, we worked together trying to prove this conjecture, but ended up with a counterexample. We adapted the example by Bourgain, fit it into every intermediate dimension, and showed that this conjecture is no longer true when n is large. It fails when n is at least 3. And it remains an open problem that for n at least 3, p greater than 2, determine the optimal exponent gamma, such that this LP Schrödinger maximum estimate holds. This problem is challenging because for p greater than but close to 2, this optimal estimate here should imply our sharp L2 Schrödinger maximum estimate. Okay. Next, we'll see a generalization of the L2 Schrödinger maximum estimate. First, we observe that by locally constant property, the L2 norm of this Schrödinger maximal function is equivalent to the regular L2 norm over a subset Y. Let's see how to find this subset Y. X in Rn, T in R. And this is the R bar in X space. And this is a time interval from 0 to R. By locally constant property, the absolute value of the Schrödinger solution is essentially a constant. So for any lattice unit cube in X variable, we can find a unit cube in space-time lying above it, such that inside this unit cube, the absolute value of the Schrödinger solution reaches its superimum value over the time interval. Okay, and we can do so for every lattice unit cube. And in this way, we find a subset Y, satisfying the following properties. On this subset, the absolute value of the solution is reaches the maximum value over the time interval. And for each lattice unit cube in X variable, there is exactly one unit cube from Y lying above it. And by this choice of Y, we have this property. The L2 norm of the Schrödinger maximal function is equivalent to the L2 norm over Y. Okay. And we see that Y is n-dimensional because its intersection with any ball of radius R is bounded by R to the n. Okay. So the L2 norm of Schrödinger maximal function is equivalent to L2 norm of the Schrödinger solution over an n-dimensional set. Informally, we say that Y is an alpha-dimensional set if it is a union of lattice unit cubes satisfying that its intersection with any ball of radius R is bounded above by R to the alpha. Okay, and generally, we say that H is an alpha-dimensional weight if it is a non-negative measurable function and its integral with over any ball of radius R is bounded above by R to the alpha. In particular, if Y is an alpha-dimensional set, then its characteristic function is an alpha-dimensional weight. Okay. And joint with Ruixiang Zhang, we proved this weighted Fourier extension estimates. Here, alpha is any fractal dimension between half of n plus 1 and n plus 1. And we have these two equivalent estimates for functions f with Fourier transform supported on the n-dimensional unit ball. Part 1 said that the L2 norm of the Schrödinger solution over any alpha-dimensional set Y in the n plus 1 dimensional ball of radius R is bounded above by R to the exponent alpha over 2 times n plus 1 FL2. Recall that the Schrödinger L2 norm of Schrödinger maximal function is equivalent to L2 norm over an n-dimensional set. And when alpha equals n, this exponent is the sharp exponent n over 2 times n plus 1. So this is a generalization of the L2 Schrödinger maximal estimate. Okay. And part 2 said that the L2 norm of the Schrödinger solution over the n plus 1 dimensional ball of radius R with respect to any alpha dimensional weight H is bounded above by the same term, R to the alpha over 2 times n plus 1 FL2. These two parts are equivalent. Part 2 implies part 1 because given an alpha dimensional set Y, its characteristic function is an alpha dimensional weight. Okay. And part 1 implies part 2 by the locally constant property and a dyadic pigeonholing argument. This was observed in the paper. Okay. Here are some ingredients in the proof of the weighted Fourier extension estimate. We used a broad narrow analysis. This broad narrow analysis appears in many others' work on Fourier restriction problem. In the broad case, there is some multilinear structure, so we can apply Banach-Cabarré-Tau's multilinear restriction estimates directly. And in the narrow case, the contributing frequencies are concentrated around a subspace of a lower dimension. So in this case, we can apply Bogin-Dimitrov L2 decoupling inequality in that lower dimension and do induction on scales. Okay, this is a weighted Fourier extension estimate that we proved. And the speaker constructed some examples showing that this estimate is sharp when alpha is large. It is sharp for alpha between n and n+1. And this weighted Fourier extension estimate has several applications to problems in PDEs and geometric measure theory. We already saw that the case alpha equals n is a generalization of the L2 Schrödinger maximal estimate. And for general alpha, it relates to spherical algebraic decay rates of fractal measures and sets of divergent set of Schrödinger solutions. And for alpha close to and greater than half of n+1, this estimate applies to Falconer's distance set problem. And we'll see more details soon. Okay. To get some sense why this weighted Fourier extension estimate has such applications, let's see a classic result by Frostman. He said that given a compact set in Euclidean space with positive alpha dimensional Hausdorff measure, there is a probability measure mu supported on it, such that the measure mu over any ball of radius r is bounded by r to the alpha. Such a measure is referred as alpha dimensional Frostman measure. This alpha dimensional measure corresponds to the alpha dimensional weight after a rescaling. And because of this lemma, the weighted Fourier extension estimates applies to several problems concerning the Hausdorff dimension. Let's see the applications. The first one is a divergent set of Schrödinger solutions. This question was proposed by Hergren and Herlin. This question is a generalization of Carlson's pointwise convergence problem. Here, given an initial data f in the Sobolev space Hi of Rn, we take this divergence set, the set of all the points x, where as t goes to 0, the solution doesn't converge to f of x. We know that when the regularity s is large enough, we have pointwise convergence. So the divergence set has 0, the bigger measure. But how small can it be? Here we take its Hausdorff dimension and then take the supremum over all the functions f in Hi of Rn. Denote this value by alpha n of s. And the question is to determine the exact value of alpha n of s, the size of divergence set. Okay. By the works of these authors, alpha n of s is known if s is large enough or small enough. If s is large enough, the solution converges everywhere, so alpha n of s is 0. And when s is small enough, the pointwise convergence fails. So the divergence set has positive the bigger measure, and alpha n of S equals n. Well, for S in between, it's still open to determine the exact value of alpha n of S. And our weighted for extension estimate gives an upper bound here. In particular, when S is greater than this sharp regularity n over 2 times n plus 1, this upper bound is smaller than n plus 1 minus 1, which is n. So alpha n of S is smaller than n. The divergence set has 0 the bigger measure, and it implies the pointwise convergence. Another application is a spherical average Fourier decay rates of fractal measures. This concerns the decay of the Fourier transform of a fractal measure. Suppose we have a fractal measure supported on a hyperplane. Then, in this normal direction, the Fourier transform mu hat is a constant. There is no decay as c goes to infinity. Well, Mattila observed that if we take the average value over sphere instead, then as the radius of the sphere goes to infinity, we can expect some decay rates. Okay. So we want to prove an estimate of this form. Here, mu is any alpha dimensional measure inside the d-dimensional unit ball. And we want a decay estimate like this. The L2 average of the Fourier transform mu hat over the sphere of radius r is bounded by r to the negative beta. Okay, the question raised by Mattila is to identify the precise value of beta d of alpha. This beta d of alpha is the optimal beta for which this decay estimate holds. So beta d of alpha represents the spherical average Fourier decay rates of all alpha dimensional fractal measures. In dimension 2, the exact decay rates are known. When alpha is smaller than 1, this result is due to Mattila. And when alpha is greater than 1, this result is due to Wolf using a bilinear restriction method. In higher dimension, when d is at least 3, for alpha smaller than half of d minus 1, beta d of alpha is known due to Mattila. And for alpha greater than half of d minus 1, beta d of alpha is still a mystery. When alpha is between half of d minus 1 and half of d, the best known lower bounds for the decay rate is due to Mattila. And when alpha is greater than half of d, the weighted for extension estimate proved by Ruixiang Zhang and myself gives this lower bound for the decay rate. Okay. And there are also some examples constructed by the speaker, which gives the best known upper bounds for the decay rates. Okay. Another application is the Falconer's distance set problem. Given a compact set E in Euclidean space Rd, we consider its distance set delta E. It consists of pairwise Euclidean distances between points in E. So delta E is a subset of R. The intuition is that if E is large enough, then the distance set should also be large. And based on an example constructed around lattice points, Falconer proposed this conjecture. It said that if the Hausdorff dimension of E is greater than half of D, then its distance set has positively bigger measure. Here, D is at least 2, and this conjecture is still open in all dimensions. Here are a few landmarks. Falconer himself proved that if the Hausdorff dimension of E is greater than half D plus 1/2, then the distant set has positively bigger measure. Since then, this dimensional threshold half d plus 1/2 has been gradually lowered. It was lowered to half d plus 1/3 by Wolf in dimension 2 and by Erdogan in dimension 3 and higher. And this threshold was further lowered. It was lowered to half d plus 1/4 plus a small number 1/AD minus 4 in these two works. When d equals 3 in this joint work, we used a similar proof as that for L3 Schrödinger maximal estimate. And in higher dimensions, this result follows from the weighted Fourier extension estimate proved by Ruixiang Zhang and myself. And in this breakthrough by Guth, Uswich, O, and Wang, in dimension 2, the threshold 1 plus 1/3 was further lowered to 1 plus 1/4. And this result was later extended to every even higher dimension in this joint work. So now in every even dimension, the best known threshold is half d plus 1/4. Okay. All these previous works used an approach developed by Matila and combined with some Fourier restriction theory. And these two recent works use a new approach developed by Bochen Liu, combined with Opland's radial projection theorem and Bogin-Dimitar's L2 decoupling. All right, that's about the applications of weighted Fourier extension estimates. And I'll stop here. Thank you for your attention.
Okay, so we are at the end of this talk. Since there is no room for questions, I think I will take the occasion and thank Xiumin again for the talk. And sorry, it cannot be a larger applause. Okay, goodbye everybody then.
Bye.
Bye.